Alrighty, hello. Today we are talking about area under the curve in regards of x. We're going to talk about area between curves, but before we jump into all of the new stuff, I want to start with some review so that these ideas are more, you can kind of grasp these ideas more, is basically what I'm getting at. So I'm going to draw an XY line here. So XY. And let's make my function purple. This is f of x. Okay. We talked about in the past, we've talked about this idea of Riemann sums, where I'm going to take the height of my curve, come down over some bound of x. So like a lot of times it's like we're going to go over 1 from 0 or 0.5 or something, but starting at this height. And we're going to repeat this process. So here's 2. Repeat the process. Here's 3. And we did this all the way down here to get a very good idea of what, or a very good estimate of what the area under the curve was between the curve f of x and our bound of the x-axis or y equals 0. When we were doing this, we realized well, this is a pretty good space, and I'm going to find that I'm going to have space in between here, even there, and I'm going to find space no matter how I do this, unless I can make these lines, like here at 1, go really, really, really small. Now I'd have to really, really zoom in to get them really, really small. And it's really hard to get to that point just doing it on paper, but the closer I can get, the more exact my area is going to be. We've definitely learned a few things because of that. So this idea of Riemann sums, we talk about, it's a summation because we're going to be adding 1, 2, 3, 4. We're going to be adding all these pieces together. So I'm going to write the book definition of Riemann sums. It is this idea when I starts at 1 to n being how many times we break it up, of our function f of x times our change in x. The function f of x here, I'm going to go in purple, this is our height. And the last part here, this change in x, or that's delta x, this would be our height, length or base, however you want to describe that, but this describes this length across. The height would be how high up we are going with the purple line there, our function f of x. And we would do this for every piece and add them all together. Well, we are in calculus now, and the idea of we move past this, we've actually learned to do something that's very similar. The reason why the antiderivative sign looks like an S is because we're adding things. We're adding things all the time. My height is still f of x, right? Because my function's my height, where I can break these things into really small pieces with a derivative of that. Well, the antiderivative of that. And this dx is saying, okay, I'm going to go as small as I can go, and I'm going to get a million lines in here. Million. Basically, as many lines as I can get in, I'm going to get in. So we have this cool little formula that describes that. Now, I did miss the limit part because I didn't talk about that, and then our bounds. But we do take bounds of where we were looking for this. If you did the indefinite, you're going to get a value, but there's no bounds. So not super helpful. But in this case, you can see here how this, again, is our height. So is this guy here, multiplied by our length, base, width, whatever you want to describe that bottom part, to get area. So that's the idea we're looking at. But to build off that, we're going to talk about looking at two functions and how we can find this area between them, this green area here. So what I got down there says this: consider two functions that are continuous on the interval a and b. A being here, b being there, and for each one, they're all the same from -1 to 1, but in this case, I want to talk more generally. The region between the curves can be found by subtracting the area of the upper region. So this area, this upper region, or if we look at the upper region, we're going to look at the curve that goes up. That's on top. It's this area of the upper region, subtracted by the area of the lower region. Wait, whoa. Okay, subtracting the upper region, sorry. I was like, where am I going? By subtracting the area of the upper region and the area of the lower region. So we're going to subtract the two. This one being like this minus this. And it's pretty visual with this picture. So if I look here, we can see that if I was going to take this whole thing, it looks exactly like this. And if I look at this piece here, it looks a lot like this piece here. And the reason why it is because it is that piece. So just reading off those words, those definitions on top, we can get to the point of, okay, well, if I want to find this region in between, I'm going to take this area under my first curve. So b with my bound, or the antiderivative of my bounds of a to b of g of x dx. I can subtract the antiderivative of f of x with those same bounds. Finding that different idea. We can even rewrite this to simplify it even more. So, rewriting it here, it's going to be the antiderivative from a to b of g of x minus f of x dx. The reason why we can do this is because we have these same bounds here. And we are using the same variable of x. So we can just put them together in one piece then. Okay. We're going to use this one more often than not, just because it's simpler. We only have to take one antiderivative. And that way we're not trying to do 20 things at once. So, alrighty. Well, let's figure out what our area between those curves are. In any case, our top curve in this one was g of x. So we'll start with g of x. G of x is negative x squared plus 6. We can also put in our antiderivative, so let's do that before we forget. The antiderivative, our bounds, like I described before, are -1 and 1. So -1 and 1. And you're going to do this, the bounds, in the type of way that the lower number is on the bottom, the higher number is on top, always. Just in case you were wondering. So we're going to subtract the function of f of x. F of x is x squared plus 1. So we get x squared plus 1 dx. Alrighty, quickly I'm going to simplify. So take the antiderivative from -1 to 1. We have negative x squared minus x squared here. That's going to give me negative 2x squared. And then on the other side of that, I get plus 6 minus a positive 1. So plus 5 dx. Awesome. We're at the point here where we can't simplify anymore, so let's take the antiderivative. We're going to do it piece by piece. So doing the first piece here, the antiderivative, the negative 2 is going to stay the same. We're going to go up in a power, so x to the third, and then multiply by the reciprocal of the power, 1/3. Perfect. We're going to do the next one. Next one is 5. The antiderivative of 5 is 5x. Nice and easy. From there, we're going to take our bounds, plug those in there. I'm going to quickly simplify this just one last time to make it a little bit easier. So it's negative 2/3 x to the third plus 5x from the bounds of negative 1 to 1. Let's test that here. For negative 1, we're going to get negative 2/3 times 1 to the third plus 5 times 1. And for negative 1, we're going to get minus the entire piece of negative 2/3, negative 1 to the third, plus 5 to the negative 1. Quickly simplifying here. Whoa, I don't want those colors, I want that one. 1 to the third is going to give me 1. 1 times negative 2/3 is negative 2/3. 5 times 1 is 5. We're going to get negative 1 to the third, which is negative 1. Negative 1 times 2/3 is positive 2/3. Minus 2/3 with the minus sign. So minus 2/3 again. And the last step here is 5 times negative 1, which is negative 5. We have to do the minus sign there as well. So it's going to be plus 5. Simplify it out, we're going to get 10 minus 4/3. If we put 10 in terms of thirds, we're going to get 30 over 3. So 30 minus 4 is going to give me 26/3. Yes, we could simplify that more, but we're at a good place there. So this idea isn't too scary. We just have to do some simplification, subtracting, and then just keep track of our negatives to make sure we're getting our right answer. It can get tedious, but I think this idea isn't going to be too scary for us. So awesome. Let's move on to the next example. It says, let R be a region in the first quadrant enclosed by the graphs y equals 3x and y equals x squared. Here we have both those graphs. I've had those drawn. So what I like to do right away is ask myself 2 questions. Or write down a couple things first, I should say, not ask questions. I know I'm taking the antiderivative if it's a region between curves. So I'm going to draw my antiderivative sign. Next, I'm going to see which function is on top of my area. So my region's here. If I look on top, top being up, I can see that the green line is on top of the reddish pink line. So I know that I have to do the top minus the bottom. So the top function is actually going to be our green function there. So 3x. The bottom function is going to be our x squared. And that's both our functions. Next, I look at my bounds. It says I'm bounded by the first quadrant here. So knowing that, I know this bound here has to be at 0, my lower bound. That's a weird 0. Sorry, 0. My upper bound is actually where they intersect up here, which we kind of see. We can calculate this, but because they give us a graph, we can just look at it. it's going to be at the point 3, 9, looking at this piece here and this piece here. We are going to use the x coordinate in this case. So it's going to go from 0 to 3. First thing I always look at here is, can we simplify this? Can we combine like terms? Can we do anything with that? The answer here is no. We are perfectly ready to go straight into taking the antiderivative. Doing that there, 3 is going to kind of stay the same, and we're going to go up in a power with our x. So x squared, because we went up in a power, we have to multiply by the reciprocal of the power. 3 times 1/2. The second one there for x squared, we're going to go up in a power and then multiply by the reciprocal. And we're going to take that from 0 or 3 to 0 and subtract our difference. Simplifying this, I'm going to get 3/2 x squared minus 1/3 x cubed. Again, from 3 to 0. Doing for 3 here, or plugging in 3, we're going to get 3/2 x, well, not x, sorry, we're plugging in for x, 3 squared minus 1/3 3 cubed. Awesome. It's minus our next part here for when everything equals 0. Looking at this, we can do it really fast. 3/2 0 squared. We'll do that first. Minus 1/3 0 cubed. Right away, we can kind of identify that this whole side, we get 0 times something minus 0 times something, so we actually just have minus 0 on this side. If you need a second to look at that, take your time, but we can see that right away. Next, on the left side, we can kind of keep moving. On the left side, we're going to get 9 times 3 over 2 minus 3 cubed. So 3 times 3 is 9, times 3 is 27. So 1/3 times 27. Doing this here, 9 times 3 is 27. I have 27 over 2 minus 27 divided by 3 is going to be 9. I can make that go to 27 over 2. We can put 9 over 2 by doing 9 times 2 over 2, which would give me 18 over 2. So because we're subtracting fractions, we're just going to subtract the numerator. 27 minus 18 is going to give me 9 over 2. And that's for this problem. Kind of an easier example, but I want to get used to finding these points here and looking at these different ideas of, okay, can I simplify? Simplify this. Identifying when something's going to give me just 0. And then doing our full subtraction using fractions a lot of times. So, awesome. Got one last example here. Example. Let R be the shaded region in the first quadrant enclosed by the y-axis. And the graphs y equals sine x and y equals cosine x, as shown in the figure. Okay. Sorry for my yawn. It's early. Okay, so looking here, we have this point in pink. Well, how can we find this point in pink? How do I know when two lines are crossing? How do I find out that spot? The answer to that is, well, we have to set them equal to each other. So cosine of x is equal to sine of x. Here, this is harder than it looks. It's actually also easier than it looks. If you remember your pre-calculus days, we've talked about something called the unit circle, where I'm going to draw my main ones in. This is pi over 2. This is 0. 3 pi. over 2 pi. And we need to figure out when our x and y coordinates are going to be the same. And it actually happens twice on the unit circle. You can also play around on your calculator. That's probably how I would have approached this the first time. But here, this point here, it actually happens. Square root of 2 over 2, square root of 2 over 2. This is halfway between 0 and pi over 2. This point here is pi over 4. So when I do plug in, or when I do solve this, x is going to equal pi over 4. When I plug in x for cosine or sine, I get square root of 2 over 2. Cool. So we found our bounds. Our bounds are going to be 0 and pi over 4. So let's write it. The antiderivative of 0 to pi over 4. Let me make that prettier. Pi over 4. Easier to read. Here, which one is our top function? Is it going to be sine of x? Or is it going to be cosine of x? It's like cosine of x goes there, while sine of x goes underneath. So, looking at that there, we're going to start with cosine x. So we have cosine of x minus sine of x dx. Is there anything we could do to simplify? In this case, we cannot. So we're going to take the antiderivative. What do I take the derivative of to get cosine? Or what is the antiderivative of cosine? Is sine of x. This one is tricky. Take a second before you do it. What is the antiderivative of sine? It's going to be positive cosine of x. Because when I take the derivative of cosine, I flip my sign and get the sine. Nope, no dx, sorry. And I'm going to take these for my bounds of 0 and pi over 4. Okay, going from there, let's start plugging things in. So sine of x, or sine of pi over 4, sorry, plus cosine pi over 4 minus sine of 0 plus cosine of 0. Get to the edge of my paper, sorry. Here, we know that on the left side it's going to be the square root of 2 over 2 plus the square root of 2 over 2 with these two. We're going to be minus, oops, I'll switch colors quick. Sine of 0, cosine of 0. Well, at 0, my point is 1, 0. With cosine being first, so this would be minus 0 plus 1, or just minus 1. Putting these two together, because we're just going to keep simplifying, I'm going to add the tops. When I add two square roots of the same base, I can actually just put a multiple in front. So because I have 1, 2, I'm going to have 2 square roots of 2 over 2 minus 1. Well, I have 2 and 2 on the top and bottom of my fraction, so those can go away. My answer is going to be the square root of 2 minus 1. And that is going to be our answer for that problem. So going through these examples, we're seeing how to find these area between two curves. In this case, we'd usually say like unit squared because it's area or something like that. But because they're graphs, we actually just leave them as the numbers. So I hope this was helpful than just sending more of the notes to you guys. Let me know if you have any questions on this. We can always touch base, but this was our lesson over how to find the area under the curve in regards to x, with also regards to area between curves. So hope you have a great rest of your day.